Good morning, and welcome to another wonderful day in the world of chemistry. And I'm your host, Mrs. Robinson. Yay! Um, Welcome to part 3 of the Unit 2 test. We've already introduced, definitions and what a solution is. We talked a little bit about concentration and calculated how to dilute solutions. So let's talk about that concept in and of itself, solubility. What is that? Okay, well, solubility is literally the amount of solute it takes to saturate. So remember when we were talking about a saturated solution? Well, depending on what the solute is going to determine how much can be dissolved. And here we also use terms like soluble and insoluble. And basically, as you can see by the slide, solubility rules basically are given to you. Okay, this is not something you should have memorized. You can use this one. This is the one from the test. And it's just, you just literally just kind of read it. Or my favorite, I'm going to go right over here because we don't need the activity series. This is my favorite right there in the middle. This is that star chemistry one that I sent you. And look, here they are. It's telling you what is actually soluble compounds contain these things. Common exceptions. If any of these are attached to this, it becomes insoluble. These are insoluble compounds. And then here it tells you what the exceptions are. Okay, and why? Well, because if you notice, there is a fun little question hidden in this particular problem. All right, let me scooch myself back over here. All right, and what is that problem? It's right down here. Guess what time it is? It is Mrs. Robinson's makeshift document camera. No. There it is. That is the equation that was on the slide. So, what do? Well, we got to harken back to the days of, I'm not going to use all the different colors again. We're going to harken back to the days of last semester when we talked about the different types of reactions. And hopefully you all notice, what is this? Yeah, everybody scream it to the screen. Yeah, it's a double replacement, double displacement reaction. And what does that mean? It means that it is prom date swap night. It is date swap. Okay, so what you see here is this right here. Yes, it is good news. And what you see here, that means aqueous. What that means is it's a solution. What does that mean? It means that it actually was able to dilute itself. It was able to, it was soluble. Okay, so next step is we got to play the flip-flop game. Swap dates. We have this and we have this. This is a metal. This is a metal. We got this and we got this. This is a non-metal. This is a non-metal. Two non-metals, to be exact. That is a polyatomic ion. Okay? So remember that when swapping, they cannot go, like, you can't put a metal and a metal together. That's a no-no. What you have to do is you actually have to, you literally just swap the dates. So let's keep sodium here. Okay. And he's going to swap with magnesium state and become, ooh, that looks familiar. And here's magnesium. And he's swapping with sodium state. Ooh, look, now we have new couples. Just like Brangelina. Now we got new couples. We got sodium chloride and we now have magnesium hydroxide. Ooh. Okay, so what does that mean? I'll tell you what it means. We end up with NaCl and magnesium hydroxide. And, you know, yes, we could balance it and all that fun stuff too. But the main thing that I want us to look at is, go up here. You see where it says soluble salts? Read rule number 1. What does rule number 1 say? It says the Na plus, sodium ion, potassium ion, and ammonium ion form soluble salts. Thus, NaCl, KNO3, NH4SO4, Na2S, and NH42CO3 are soluble. Translation, salt, it's soluble. It stays in solution, so it's going to stay as an aqueous. What about this one? Magnesium hydroxide. It says sulfides are usually insoluble, except, well, we don't have one of those. Let's see, where are we? Let's look at number 2. That one doesn't apply. Look at number 3. Chlorine, bromine, iodine. That doesn't apply. That doesn't apply. It doesn't apply. Number 2 doesn't apply. Hydroxides are usually insoluble. Exceptions include NaOH, KOH, strontium hydroxide, barium hydroxide, which are soluble, and calcium hydroxide, which is slightly insoluble. Is magnesium on there? No, it's not. So what does that mean? It's not one of the exceptions. So guess what? It's a solid. And guess what that means? It's going to float and form a precipitate, and it's going to settle on the bottom. So it basically means when you stir sodium hydroxide and magnesium chloride and you pour them together in a beaker, you're going to end up with salt water, basically NaCl in the water, but then you're going to have magnesium hydroxide dribble out. Pretty cool, huh? I think so. All right, let's keep going. So we just talked about solubility. Now let's talk about things that actually can affect it. What can affect solubility? Well, again, we know temperature. If you increase the temperature on a solid, you're going to increase the solubility. But, big buts, remember, there's always big buts. But if it's a gas, like in a soda, think about it. When you heat up a soda, it decreases the solubility. It goes down. It goes down. There we go. So like backwards things drive me crazy. Pressure. It doesn't really affect liquids or solids per se. However, gas, again, soda. When you put gas under pressure, you're going to increase its solubility. That's why soda is so delicious. Henry's law states the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas on the surface of the liquid at constant temperature. Yeah, you don't need to know that. Just know that pressure affects gas. And finally, number 3, polar solutes dissolve more readily in polar solvents, but not in nonpolar. So essentially what it means is it's the same kind of scenario. You see what I'm saying? Yeah. So polar with polar, nonpolar with nonpolar. That's the rule. Polar, nonpolar, that's the rule. All right, let's see. What do we got? Okay, I got time. Oops, somebody's here. Close the thumbnail. Which brings us to Homer's dilemma. This is actually on the test, guys. And I thought it was a little, it's a little tricky, so that's why I wanted to walk you through it. It says a saturated solution of copper 2 hydroxide is prepared in a beaker by adding the solid to water and stirring. When the solution is prepared, crystals of copper 2 hydroxide remain on the bottom of the beaker. That's no good. So it says which change will cause the molar solubility of copper 2 hydroxide to increase. Okay, all fancy words, fancy words for what we just talked about. How do we increase the solubility? So I don't see in our answer choices here, there's nothing here about, there's nothing there about, I'm trying to see if I have a pointer, but that's okay. There's nothing here about, increasing the temperature or pressure or, any of that stuff. So what do we do? Okay, well, think about it. If crystals, let's go back up again. Imagine it in your brain. You got yourself a little beaker. The beaker's filled with water. You put in the copper 2 hydroxide and you're stirring and you're stirring and you're stirring, and the crystals are going to the bottom. So my question is, do you want to add more copper chloride, copper hydroxide? No. I'll give you this. Do you want to dilute it? No, we're not trying to dilute it. We want to dissolve. We want to dissolve the copper hydroxide. Yeah, guess how we're going to do that? And I know, this is why I say it's a little bit tricky. We're going to add some acid. I know, because you're just like, I didn't know that was an option. And that was my point as to why this is a little bit tricky. Because when you add that hydrochloric acid, those hydroxides are going to attract to the hydrogen, and magic happens and everything dissolves. All right, I'll see you guys for part 4.